And yes, this session I am super excited about. We have the lovely Serkan Saydam joining us today. So Serkan is currently the Chair of Mining Engineering at the School of Minerals and Energy Resources at UNSW. He's established research collaborations with NASA, ESA, and Luxembourg Space Agency, as well as more than 40 research organizations and universities globally. So a key focus of his research is to address the current needs and future challenges in the minerals industry. They are generally complex engineering problems as mining environments become more extreme and constraints are imposed due to increasing social, environmental, and health and safety standards. So with all of his expertise, I'm super excited to learn today about off-earth mining, the current status and the future. So it's going to be an amazing session. Please keep using the chat. We'll open up the floor at the end. And yes, thank you so much, Serkan, for joining. It's amazing having you here.
All right, so thank you very much, Jess, and Magic Mike was amazing. It's really, I'm looking forward to come and see you in Bondi Junction. Oh, Bondi Beach, sorry. Again, thanks for the opportunity, Jess. I'm gonna talk. It's when I speak about this topic for a while now, they ask me a lot of questions and I expect a lot of questions as well. So let's start. So you may consider that why is a guy who likes diving with a PhD in mining engineering talking to you about space? I mean, I guess the answer is, as Jess mentioned in my bio, I'm the future mining guy, and I do all of my research is in extreme environments. So I like being in extreme environments, in underground, deep underground mines. I haven't been in space yet, but I'm working on that, and also I like diving. So and also we go to the remote areas in Australia or all around the world in the mine sites. So that's my interest. So let's start with a very simple drawing that I draw, that little blue, very little blue ore body, which is subsurface, of course. And there is the surface here. And then let's say that this is called unobtainium and worth of $20 million per kilogram. So that's very, very high value of such a ore. And if we put that also very nice tree or very important tree on subsurface above this ore, how would you mine that? I hope it's not like that. And now you may remember what I'm talking about. That scene was from Avatar movie. And they try to mine the deposit, unobtainium ore from underneath from this tree. So obviously you wouldn't do surface mining with $20 million per kilogram. You could, I mean, as a mining engineer in this technology, I'm not talking about future now, I could get this ore body under this tree without disturbing the surface. So don't believe everything what they show it in the movies. Let's start it. So how did it start, this off-earth mining or space mining idea? It's basically, it started with Shackleton Energy Company. They established the first space mining company in 2007, focusing on the moon. And then Planetary Resources and Deep Space Industries focused asteroids, and all of them being funded by billionaires. And they all closed down in mid 2010s and also at the end of 2010s. So we'll come back to that. So there were a lot of interest in, after 2010, there were a lot of interest in the US about mining on the moon or asteroids. President Obama talked about, giving permissions to US citizens to mine asteroids publicly. So that created a lot of attraction especially in US business media. So let's park that and talk about the motivation. In geology or mining, we say where she be, there she be. So we can't change the location of the deposit. So there are valuable minerals to be mined, and we are adventurous humans will arrive in crowds, even combating with extreme condition, extreme environments, or an excessive risks. So, but the motivation is because of abundance of valuable resources which we can feed our technologically driven society, the necessity and demand of discovering new places that our society can colonize, and also most probably it's my biggest motivation is developing new technologies and processing to enable to achieve such missions will create spin-off technologies which it can be used for our terrestrial operations. In last 60, 70 years, there were a lot of developments for space exploration, and then recent years, space colonization has rapidly moved several steps closer, becoming more reality because of the improvements in rocket propulsion and design and all these technologies. So it's obviously, you may have heard about the Artemis program established by NASA, aiming to go to the moon again, going back to moon, and then ultimately reaching to Mars. So my dear friend Jerry Sanders from Johnson Space Center provided this slide, and they got 4 different stages of this. First of all, they want to send the human being back to moon to initiate utilization of human being on the moon and or around, and then set up this moon exploration and science and setting up all these related activities on the moon surface to get ready for the Mars travel, and then create this sustained moon colonization and then arrive to Mars. That's the focus of Artemis program, which Australia is part of it. There is a new terminology, it's called in-situ resource utilization, or simply ISRU. But in-situ resource utilization used by Americans, space resources utilization used by Europeans. It's the same meaning. What does that mean? That instead of sending the materials from Earth to the planets, Moon or Mars, then you should use the in-situ materials, local materials to sustain yourself. That's what called in-situ resource utilization. To me, it's a mining. But the creating a market is a big problem in space. So first of all, currently we only have one industry, one market in the space. So if you look at that, we only have communication satellites, right, as a business in space. So the next logical market could be tourism, which there are some attempts on that. And another one could be space, extracting space resources, space mining. And everyone agrees that space's first agreed commodity is water. Why? Because having access to water will enable sustained presence of humankind in space, and also water is necessary for life support and can be refined into rocket propellant, because H2O, hydrogen and oxygen, that humanity can further explore the solar system, use water location as a petrol station to go further. But delivering water in space is a commercial concern. So how much would you pay for a kilogram of water in space? I mean, I don't know how you're going to guess that, but United Launch Alliance, ULA, said that they will pay $3,000 per kilogram if you deliver water in space. So what happens then? Luxembourg Space Agency provided a document called Opportunities for Space Resources Utilization, and they mapped out the time frame and then the potential use and the potential resources. As I said, they focused first, they will produce water from moon in first 10 years to use as rocket fuel, petrol station. and then use as a life support in colony, and then use moon regolith, which is the dust surface part of the planets, moon or Mars, and then access to asteroid water, and then reach to Mars, access the water and raw regolith for construction material, and then access to metals in those celestial objects, and then last as a platinum group metal. So create this colony, first of all, petrol stations, and then colony, set up our colony well, develop equipments, infrastructure, and then last we bring back to Earth these resources. I'm talking about 20 plus years. That's arguable, these numbers. So the value chain of rocket propellant offers the most viable business case and the best near-term opportunity because of high confidence in demand and availability of water on the moon. So this is basically reaching out from Earth orbit to moon, use as a petrol station and go to Mars. There are near Earth asteroids, also low Earth orbit here. So the asteroids between Mars and Jupiter, I'll show you later. There are plenty of asteroids and also 2 moons of the Mars, Phobos and Deimos. So once you consider ULA buys your water, then it becomes real business. It's not science fiction anymore. So the problem here is, even though you're selling for $3,000, the launching cost is over $20,000, was $20,000 per kilogram until 2017. Until when? What happened 2017? Because of SpaceX with their new rocket system, reusable rocket, recently reduced this cost to around $2,000 per kilogram. So then becomes the real market. If you can sell it for 3,000 and the cost is of course, this cost is not only 2,000. I'm just giving a very simple calculation. So you can start developing the value calculations here. So, but SpaceX develops Starship SN-15. This cargo ship with ability to carry 100 tons of material. So much, much, much larger than many other rockets we have right now. Then they say that reducing launch cost further from $2,000 per kilogram to $100 per kilogram. So then it becomes a real business now. So it's everything changes. However, ISRU definition I mentioned before, it may be affected because ISRU may not be needed anymore because of sending from Earth could be cheap as well. Then Artemis program can fall down because of if Elon Musk or SpaceX develops this Starship, it keep failing in last couple of attempts. So water may not be that much value anymore. So that's the point. So we'll talk about that later, the other challenges as well. So when we talk about the targets, so we got the asteroids, moon, and the Mars, right? I mean, the Mars is moons as well. So these are the first attempts for potential targets. So asteroids are generally, they think that it's a rocky material, but they are also rocky, but also sometimes gas, sometimes liquid. So asteroids being classified 3 types: carbonaceous and SC. S means C type, which is carbonaceous, and S type, which is stony, M type metallic. So if you remember Don't Look Up movie, and I mean, if you watch that movie, it's a funny. If you didn't watch that movie, but I recommend. It's quite funny. They you know, the asteroid hits Earth, and you know, that's the story about it. There was one guy talk about the value of the asteroid. They try to mine. They said that quadrillions of dollars of worth of minerals in there. How correct? I don't know, but I did a study on that years ago, which we published in the high quality journal. We looked at the asteroid called 1986 DA, and this asteroid is actually look like a naturally occurring stainless steel, which is 2.3 kilometer diameter. Even if you produce all the nickel and iron ore or cobalt to make stainless steel in Earth, you can't make 2.3 kilometer stainless steel diameter mass or volume, you know. So this asteroid is very far away, 75 million kilometers away from Earth, and approximately to reach that asteroid it's about 8 months, and it's quite similar to Mars, from Earth to Mars. So if we did a couple of scenarios looking at the value, so calculate the value of the asteroid. So if we bring the asteroid, mine there and bring the material back, it's very negative value. So you see that we put it about 100 years, it's very negative. But if you don't worry about the second, it's complicated to explain, but in short term. But in second case study, what we looked at, if we bring the asteroid halfway of between current location to the halfway of the asteroid and Earth, then it becomes very economic. But we looked at other option that if you create the market and do not bring anything back to Earth, then it becomes very, very economic. So that's very positive value and net present value. So trillions of dollars value of one asteroid only. So that's, I think, explains the value, but the numbers may be discussable. Of course, it has a lot of assumptions. But by looking at this graph, you know, this figure, so the Earth is blue, orange is Mars. Between Mars and Jupiter, here is the last one is Jupiter, there are more than 3 million asteroids turning around the sun together with Earth and the other planets. So asteroids are unfortunately no longer the interest, because mining them in near Earth orbit, technically and financially not possible. Huge transport cost, and we don't have such a spaceship to make the transport. Bringing back to near Earth may be financially possible, but very risky. And also Artemis program killed the interest of asteroid, because it's all the agencies, the countries' interest went back to Artemis program. So therefore, there is no more interest, very little interest on asteroids mining. So the other object is comets. Of course, they are snowballs, but you know, they are called space rocks, but also contain a lot of icy rock, icy chunks, frozen gases, and also water. So that might be a potential target as well, similar to asteroids, but catching them is very difficult. As you see, Rosetta asteroid here, European Space Agency did it in 2015. They landed on there. So back to the moon. So Sofia is my PhD student. He's currently working in Luxembourg in iSpace. So that photo been taken by Australian Geographic. So the moon, as you know, the gravity is 1 to 6, and it's about, you know, the temperature is quite extreme, and then of course there is no atmosphere, and it's very much difficult, extreme condition to do anything on the moon. It's a high radiation, the gravity, and then dust, and then the extreme temperature difference, and so on. So as you know, between 69 and 72, 6 Apollo missions brought back about 382 kilograms of lunar rocks. And you see these six landing sites. So these couple of slides you will see sent by NASA to, we got a group, research group. So Harrison Schmitt was one of the, Jack Smith was one of the astronauts landed on Apollo 17. So I'll show a couple of other pictures. So their Apollo 17's focus was really looking at geology to obtain samples of lunar rocks, and also to look for evidence of young volcanic activity on the valley floor. You see that photo been taken by Apollo 17 crew with its angled photography. So Jack Smith took the first colored photo in lunar surface. So lunar geology studies, they did sample collection, surface science experiments, and they did some orbital science experiments. And these two samples, so as I said, they got 380 kilogram overall in six missions. And on the left-hand side, you see that it's called troctolite, and it's like a gem-like, but it's very crystallized material. And the right-hand side is the unique one, which is classified as a high titanium basalt, volcanic origin. This very last rock to be picked on the moon by the Apollo mission, they call it the children of the world rock, because they were subdivided. It was subdivided and presented to the landers of 135 countries and also the 50 US states. So the moon has regolith, can be used like a cement material, like construction material, and water, ice, hydrogen, nitrogen, oxygen, rare earth elements, yttrium, lanthanum, and samarium, which are increasingly critical in the making of high-tech products, including tablets and missiles and electric vehicles and wind turbines. And also helium-3 is a non-radioactive nuclear fusion fuel considered by some scientists as a safe energy of the future, also abundant on the moon. So it has long believed that there is water on the moon, but it was unconfirmed until 2008. So until the India's mission found evidence of water of the surface, on the surface of the moon. This was later reconfirmed by NASA's work. So currently, it's now estimated about 6 billion tons of water on the moon. And then Mars. So Mars is a bit better than Moon in terms of the environment. So because it has, I mean, first of all, reaching there, it's about 6 to 8 months. And the temperature is more bearable compared to Moon. It's because its polar region is minus 123, equator is minus 787 to 26. So like yesterday, Jess and Mike was talking about yesterday, Sydney was 25. I was in Melbourne. So it's similar temperature to Sydney, Mars during the day, could be. So there is a 14 minutes delay, but it's very excessive environment in terms of, because of 95% carbon dioxide and less than 1% thickness of Earth atmosphere. It has huge radiation. So it's dealing with radiation is a problem there. So, but the Mars, I mean, looks like, you know, the two pictures, Mars surface on the top and the bottom, Pilbara, Western Australia. It's very similar look to me. Sorry, I made a mistake. It's other way around. It's actually the top one is the Pilbara and the bottom one is Mars surface. But as I said, you can make mistakes. So it's very similar look, to be honest. And there were a lot of interest to Mars, and we sent multiple missions starting in 1960s. And some of these, you know, I mean, the last one was Mars 2020, and Curiosity is still running, Perseverance still running, and some of them all died, and they became the heritage of Mars. So I'm lucky that Sophia and I went to JPL, Jet Propulsion Laboratory, and I took myself with my iPhone this picture while they're building Mars 2020. I think it was in 1970 17 or 18, maybe 18. I can't remember very well, but you know, I'm proud to say that. So I've seen that how they built. So the Martian environment is a bit different. Mars is differentiated planet, also has a central core made of metallic iron and nickel, similar to Earth. And distinctive color of red, they also call it red planet because of the iron oxidation of iron on its surface. It also has carbonate, methane, also regolith, ice and water. And you see the interactive picture here, which is a recurring slope lineae on Mars. It's quite intriguing feature on the Mars. So Mars sometimes may have similar look rocks. In this case, look like it's a Martian igneous rock. It's been taken by Curiosity rover. This picture is very similar to Earth type of rock. So we said that what Mars has also water is mainly in the polar region as an ice form, but also in the equator region and in hydrated minerals. So, excuse me. And as you see the polar region, and this is the landing zone, this is the picture taken as ice view. It's been taken here, these pictures. So there have been more attempts on Mars than Moon to develop extraction technologies. So Honeybee Robotics developed two equipment, mobile in situ water extraction technique for mostly Mars, but could be useful for Moon as well. So it was mainly for like an auger type, but it's for exploration purpose, sampling purpose. And Kennedy Space Center, RASA, they developed like bucket wheel excavator, but it's very small scale. It's about 1 or 1.5 meter size. So, and this is for Moon and Mars again, for ice extraction. And Colorado School of Mines developed thermal heating technique, which includes series of sublimation activities. So there are not really, there is no much mining methods point of view. We are not there yet for operation development. So at University of New South Wales, Australian Centre for Space Engineering Research, which I'm also deputy director there, our unique approach is we are the only group that we putting mining engineering knowledge into space engineering. So we simply applying this knowledge to solve the problems. So we got about 20 PhD students working on various areas on, you know, mine planning, mining method selection, either optimization, selecting the right asteroids, and very different areas of looking at the geomechanics characteristics of the Moon and Mars and etc. And also developing an economic studies and also value studies and looking at royalties and taxation sort of work, as well as sustainability, how we can develop the operations in sustainably, also impact on planet as well as on Earth. So with our research, I did research with NASA by looking at developing a model. We work with MIT Jet Propulsion Laboratory and us. So we wanted to develop a Mars colony, and HubNet developed by MIT looked at what is required for human being to survive in Mars environment. And Jet Propulsion Laboratory developed the mission model, architecture model, and I developed the economics model. So we developed a software called Water Extraction Mars Mining Model, which is basically answering the question of how many people you can send to Mars to establish colony and how many of them could work in the operation. So that's a very assumption based, but you can add some numbers and calculate things. And to find out, looking at, the Honeybee Robotics, the Misbet robot or tunnel boring machine like direction drilling. And then this interested Kennedy Space Center, and we worked with Virginia Tech and developed Mars mining operation optimizer for in-situ resource utilization. So in this one, you can add your own equipment and you can add your own deposit, you can add your own topography. So we did a more advanced. So first software we developed, it's publicly available. This one is only for NASA because it's been funded by the American government. So talking about the challenges. So obviously there are lots of challenges, but I classified these challenges as technical, financial, legal, and environmental and ethical. Let's talk about this a little bit. So geological knowledge. So in this geology, geo is Earth terminology, right? But planetary geologists, scientists, they accept the geo word to be used for planets as well. So don't worry about using geology terminology. So the lack of geological knowledge is quite obvious because we don't have any drilling data. Only we drilled 10 centimeters so far on Mars. We didn't drill anything. We did some GPR tests and seismic tests on the moon. That's it. We got hyperspectral images and we got only photos to get the knowledge of geology. So infrastructure and technology challenges are quite obvious. So how are we gonna apply the technology? What technology and infrastructure, how are we gonna develop? Are we gonna bring from Earth or we do 3D printing or something else? So that's other issues, and power and propulsion and running the operation there, it's a huge issue. As I mentioned, that landing and launching, landing is very much difficult with the rocket systems, and launching is a huge cost as well as the rocket systems. And life support of colony and radiation effects, low gravity effects, if the human being stays longer there. Currently only one astronaut stayed 1 year in the space station, not on any planets. So we don't have really experience of how human being will be affected. So financial challenges. So who's gonna fund? How it's gonna cost? How are we gonna sell it? Where are we gonna sell it? These are the big problems, of course. And supply and demand, it's very not easy because, platinum is very expensive in Earth because of scarce, because of very rare. And if you keep bringing platinum very easily, it's gonna affect of supply and demand of Earth. So it's gonna affect a lot the world economy as well. It's bringing back option is not a good option yet. We don't have regimes for this. And obviously, when I say the regimes, of course, it's huge legal challenges. So obviously, the Outer Space Treaty signed in 1967 was negotiated during the Cold War to govern space activities. And it consists of 17 articles outlining permissible actions and in space, but also lack specific consideration of mining space resources. This also led a lot of ambiguity, as well as specifically articles 1 and 2 concerning the principles of freedom of use, the benefit of mankind, and non-appropriation of in outer space. So because of this, there was a lot of debate about the legality of space resource extraction and utilization, and how this treaty would be effective by considering this is a question mark. And this debate is driven by differing perspectives between the industrialized nations focusing on exploitation and other countries emphasizing global benefit sharing. So therefore, that become the common heritage of mankind. and recent developments like Artemis Accords, as well as the Working Group on Space Resources, established. These are currently the big debate and discussion between the countries involved. So it's summarizing what we're gonna extract. First is water, then the others. And no, we're not bringing back to Earth yet. Who's gonna do it? First of all, currently there are 7 agencies, government-owned agencies. The obvious one: NASA, European Space Agency, JAXA, Japanese, and Israel, Luxembourg, Chinese, and Indians, quite active. And by looking at the history, first flying man in 1600s in Istanbul, Hazarfen Çelebi, and then Montgolfier brothers in 1700s, first hot air balloon, and then the Wright brothers in 1900, first power aircraft carried humans. So they were all individuals. So why not the private sector, right? So they are the lead companies, not necessarily all of them space mining, but as I said, Honeybee Robotics and SpaceX are focusing. So ULA, Lockheed Martin, Blue Origin, they are rocket launching and space technology countries. Gilmore Space and Fleet are Australian companies, very active and successful. And these are the companies, all of them American-based, except iSpace, TransAstra, Off-World Industries, Off-World, Astroforge, Astro Mining, Planet Mines Corporation, current space mining companies. iSpace is Japanese, but it's operating in Luxembourg. So that's the most asked question to me in discussions. To me, in next 10 years. Why? Because of Artemis program. And NASA's Artemis program really created a lot of excitement because they will send first human being. First, they will send back human again to the moon. First woman and the next man on the lunar South Pole, close to the Shackleton crater, which they consider that the water, ice is there, and perhaps the other minerals. They want to do that in 2024, 2025. It was 2024. I think they changed the date to 2025. And European Space Agency's Moon Village and Heracles mission scheduled for 2028, which is robotics, not with men, but they want to really establish the Moon Village. There are beautiful designs in the web. You can see it. You can see the European Space Agency and NASA, and they want to establish this Moon Village. And they got pretty nice pictures about the accommodation and people staying there. So especially European Space Agency's website has a lot of good pictures. Or I'm not sure how much you watch about For All Mankind in Apple TV. So they already did the space mining in Shackleton crater. They found water as well as lithium. So that's pretty good show. It's pretty realistic. I'm really impressed about that show. And as a conclusion, space mining really offers a unique opportunity to supply Earth sustainably with unlimited minerals. So as you know that minerals are not sustainable on Earth. Operations are sustainable, mining operations are sustainable because it's not unlimited. So, but in space could be unlimited, as I mentioned, Moon, Mars, asteroids, and further for humankind. So resource extraction in space or space mining is inevitable, according to my opinion, to support colonization, and therefore regulations must be established before extracting begins. So if you look at first in, first served access to resources, wouldn't promote sustainable operations, may create problems and conflicts. So as international collaboration, therefore, is quite necessary to develop the most beneficial and acceptable approach for off-Earth mining for humanity development. So finally, we're running, I don't know where you are right now. If you are in Perth, we're running Off-Earth Mining Forum West. We generally run it in Sydney. This time we're doing in Perth in 22nd of August. If you're interested, I recommend you do register, and sponsored with the companies, as you see, as I mentioned, Fleet. And this picture, I've put it at the last and second last. So Harrison Schmitt, Jack Schmitt, as I said, is the first scientist and the only scientist and geologist landed on the moon in Apollo 17, as well as previous in human history. So I'm part of a research team which we share the information. So Jack Schmitt sent actually this in November to the group, these pictures, as I showed you the other pictures as well. So he threw the geology hammer on the moon surface. You see the space, and he took that picture, flight of the geology hammer. I thought it's very relevant to this group. You may enjoy seeing this, and feel free to use it. And thank you very much for the opportunity again. I hope it will fulfill your expectations. So I try to cover really what's the status, what's gonna be the future, according to my humble opinion. If you got any questions, I'm happy to answer. Thank you again.